Hey everybody, Bill Sky, the assembly guy, back with you with another video on assembler language, and now it's going to get interesting. We're going to be talking about the central processing units, the CPU's registers. Now I have it listed here or written here as hardwired variables, and I think you can kind of say that. It's not quite that, but they're actually variables that you cannot change their name. They're the place in the CPU where you store data, to do arithmetic on them and to manipulate the data, which is everything that a computer program is all about. So let's go through a little bit of lecture here so you can understand, and then we're going to have a lot of demonstration. What we're going to do is we're going to do a demonstration in Windows, and we're going to do a demonstration in Linux. And there's also going to be another video on the CPU registers for ARM processors. So that's coming up as well, but in a different video. So let's just get started on this whole concept of CPU registers and what does it actually mean. So a CPU register, it's a hardwired variable. It's actually built into the CPU with transistors and all that stuff. It's etched into the CPU chip. These are used to store data, to manipulate the data, to do arithmetic, to indicate the status of the CPU. So the CPU is not programmable from the point of view where you can add code to the actual CPU. So you really can't create your own variables, but all of these registers, including flags, which tell you the state of the central processing unit, are actually hardwired into the CPU. I like thinking of the CPU as the brain of the computer. The arithmetic logic unit is and the floating point unit and the control unit are areas of the brain. The registers are short-term memory, and a computer's main memory is long-term storage. While the computer's turned on, remember, memory is not long-term, by definition of that term, because when you turn off the computer, so secondary storage, which would be a hard drive, a USB thumb drive, an optical drive, something like that, would be real long-term. But in the case of talking about the CPU as the brain, that's what it's all about. Now, there are a number of different types of registers. There's general purpose registers, there's special use registers, and there's also a flags register, or what they call an E-flags register. And the general purpose registers are usable by the programmer. So let's take a look at the 32-bit registers, and then we'll take a look at the 64-bit registers. So the general purpose registers that you can use in a 32-bit application is EAX, which is the accumulator register, ECX is the counting register, EBX is the base register, EDX is what they call the data register, EDI is the destination index register, and ESI is the source index register. Now that might all be kind of confusing. What are all these different things used for? Well, the first four, EAX, ECX, EBX, and EDX, you pretty much can use those any way you want. They're four variables in the CPU. They're there for the take and or for the use. Now, EDI and ESI, those are kind of specialty registers. You can use those like the other registers just for any general data, but you have to be careful because those are actually targeted as registers where you put the address of a variable, or you put the pointer of a variable or data into those registers. Not all the time, but there are some statements or commands, syntax in the assembler language that require those registers to be used for indexes or for addresses. Now, here's where it gets kind of weird. The general purpose registers, the first four, you can split those up. Now, this is a compatibility problem way back in the 80s, 1980s, where we had 8-bit registers and then soon after that 16-bit registers. And these applications may still be able to run on Windows. So Intel and AMD, they came up with this way of splitting up the larger registers into smaller registers. They can be used by these older programs. So EAX is a 32-bit register, and the bottom half of EAX is called AX. That's a 16-bit register. The bottom half of AX is AL, and the top half of AX is AH, and each one of those are 8 bits. Now, these are not separate registers. They're actually part of the same bucket of data, but it's subdivided. So, for instance, if I wanted to put a character into EAX, if I'm only dealing with 8 bits, which happens a lot with strings and C strings, You just put them in AL or AH. You don't worry about putting it into all of EAX. And there is some syntax that requires these smaller registers within the assembler language. So they're basically just divisions in the EAX register. And we're going to see a demonstration of this in both Windows and Linux. And these subregisters, as I said earlier, they're used to store smaller data. But remember, AL, AH, AX, they're all part of EAX. So if I change anything in AL, it's going to change the overall 32 bits of EAX. It's going to change the entire thing. Now, that doesn't mean it's going to change every bit. It just means it's going to change that 8 bits within EAX in the case of AL or AH. The main 4 general purpose registers that have this capability is EAX, ECX, EDX, and EBX. All of them can be separated. So effectively, if you're dealing with a lot of 8-bit data, ASCII characters, you basically have 8 registers now. Because you can use the 2 smaller 8-bit registers for EAX, ECX, EDX, and EBX. So that's 4 general purpose times 2 is 8. So that's 8. So you can do pretty much stuff with it. Now, before anybody asks, no, you cannot access the upper half of EDX, ECX, EBX, or EAX directly. It seems kind of like a waste. It'd be nice if they had a upper EDX, that's 16 bits to the left of DX, but no, you can't. They don't have that capability. You can shift all that data to the right into DX in this case, but that's something that we'll talk about later on when we talk about shift and rotate instructions. There's some special purpose registers. There's the ESP pointer or the ESP register that points to the top of the stack, and we'll be talking about the stack very soon. We have the EBP, which says what is the base of the stack, what is the first part of the stack my function can use, and what's the maximum it can use, or where its current top is. And then EIP, that's the instruction pointer. That tells the CPU what line of code you currently have ready to execute in the CPU. So your code is just data. And there's got to be a pointer that points to each line of code as you're getting ready to run it. And that's what the EIP, the instruction pointer, is all about. Then we've got some other registers. We've got the CS, which is a pointer to the code, the beginning of your code segment where your actual logic is. The DS, which is the pointer to your data segment. And then the SS, which is the pointer to your stack segment. And these segments are different parts, different sections of your code. And the CPU or the operating system needs to know where each one of those begins, so it knows where your code is located, where your data is located, and where your stack data is located. So that's the 32-bit registers. What about the 64-bit registers? Very, very similar, but with some little caveats and some extra stuff. So if you notice, the 64-bit registers all look the same except for that first character. For instance, the accumulator register RAX in 64-bit is called EAX in 32-bit. So all you have to do is change the E to an R or the R to an E, depending upon if you're going from 32 to 64 or 64 to 32. Now, why do you care about this? Well, what if you've got an older 32-bit application that you've been using that you would like to convert to 64-bit? Well, you just search for all EAX and change it to all RAX, and a lot of times that's all you need to do is just change your register names. So again, all of the E's from 32-bit registers are replaced with R's, and now you have 64-bit registers. But 64-bit's kind of cool. You've got additional registers. You've got R8 through R15. Those are additional general purpose registers that you can use to store data. Makes it a lot more ARM or MIPS like. There's just a lot more space in the 64-bit CPU to store additional data to be able to work with it. Now, the 64-bit CPUs are split up just like the 32-bit at the EAX level, but then there's also another upper level, which is the 64-bit. So RAX in this case, the bottom half of RAX, the bottom 32 bits is called EAX. The bottom 32-bit or 16 bits of EAX is called AX. The bottom 8 bits of AX is AL, just like in 32, and the upper 8 bits of AX is AH. So it's, again, these are not separate registers, but they're sections of the larger register. They're named that way. And again, they did that for compatibility, and also so you might be able to have more registers if you're dealing with smaller data. So I think what we should do is jump right into taking a look at how this works, and I really recommend that you follow along with me on this, and this is where the fun begins. All right, let's get going on our 32-bit Windows demonstration. Right after this, we're going to do a 32-bit Linux demonstration. It's almost identical to the Windows, except we have different tools. And then we're going to take a look at the 64-bit stuff. So I actually have Visual Studio 2022 here. I'm going to create a new project. We can never create too many new projects. And I downloaded all those templates that I made available to everybody. And what I'm going to do is I'm going to select the, let me see, where is it? Oh, there it is, the Komanetzki 86 functions template. I'm going to call it x86 registers demo. Okay, and when Visual Studio is done getting its act together, we're going to go ahead and take a look at the source code. And let's start seeing what we got here. So what I'm going to do is I'm going to create a whole bunch of statements, program statements that are move things into registers so we can see how they're affected, and then we're going to take a look at those in the debugger. Now the Komanetzki's template, I've got a lot of stuff in here just as demonstration. So what I'm going to do is I'm going to delete everything I don't need. I always like to have a welcome and, you know, program ending, have a nice day. I'm going to get rid of all this data. We don't really need it. And a lot of code, demonstration code in the template. So let's get rid of all of that. All right, great. So again, all I did was I just left the welcome and the end message, and then I've got the statements to produce those. Now I'm going to save and build this and make sure it runs okay. Well, we got a little bit of a problem here. Oh, I never installed the Komanetzki libraries. Oops. I never actually put those into my C drive. So let me go ahead and do that, and we'll continue. Well, after some checking, I did install the Komanetzki libraries on this. This just drives me crazy. This is a 32-bit template, but it kept it at 64. So you've got to remember to do that. I paused the recording, and I just spent about 10 minutes figuring out that I didn't drop down the x86 because the templates didn't get saved. Or I should say the template didn't get set to the correct x86. So I went ahead and dropped that down to x86, and let's see if it now builds okay. And it builds just fine. Microsoft, hello, it might be a good idea to go ahead and fix that when you have templates on Visual Studio 2022. All right, so I'm going to go ahead and start without debugging. And there we go. Hello world, program ending, have a nice day. So that template works great. All right, so let's do the next thing here. Let's go ahead and I'm going to create a statement. I'm going to move some data into EAX. So I'm going to move into EAX, and let's put a double word in there. So that would be 4 bytes or 8 nibbles. So I'm going to say 0, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to put in all F's hexadecimal into EAX. That's going to turn on every single bit. Now we could demo it at this point, but let's not do that. Let's go ahead and put in some more statements. What we're doing is we filled up all of the bits in EAX. Now what we're going to do is that we're going to move into AL. That's the lower 8 bits of EAX. We're going to move into AL 1, 1. And then we're going to move into AH 2, 2. So you'll see how it changes EAX overall. So let's go ahead and save and build this. And let's debug it. And we'll click Start Debugging. Okay, let's put a breakpoint right over here on this first no-op. And yep, so what just happened just now? Well, I forgot to put a breakpoint in my program, so the program just ran. So let's go ahead and we put that breakpoint. Now let's go ahead and say start debugging. And there we go. Now we have the memory tab up, but we don't have the registers tab. So debug Windows registers, and there's our registers. So let's start going. Okay, so we're going to go ahead and print our welcome message. And now we're going to move all F's into EAX. And you can see EAX right now has all F's in it. Every bit is turned on. I would love to show you that in binary, but Visual Studio doesn't allow that. So now we're on line 23, and let's move 11 to AL, which is the far right, which is the lowest bits, the lowest 8 bits of EAX. And you can see now all of EAX has changed. The overall value of EAX as a whole has changed. AL has a value of 11. The next thing we're going to do is we're going to move 22 hexadecimal into AH, which is just to the left of AL. So it should be now all F's 2211. And let's step over. And that's exactly what we have. So AL are where the 11s are, AH are where their 2s are. And you notice my choice of literals that I'm putting in there makes it very, very easy to tell what's happening inside the register. Okay, so let's go ahead and stop the debugging, and let's do some more. So let's go ahead and clear out. Oh, wrong place. Let's go up here, and I'm going to move into EX. Let's move all F's again. And then I'm going to move into AX. Let's put all 3s. So let's see how AX works. Now, while I'm in the editor, I'm going to go up into debug and I'm going to click toggle breakpoint. For some reason, the cursor is just not behaving the way I wish it was. So I can't really click on this column right here. I don't know why. And the reason I'm going up to the debug is because I can't click, but it's kind of nice that I can actually do it from the menu. So I went ahead and put a breakpoint on that, and I've got my breakpoint on the no-op. So let's go ahead and save and build that. Okay, and let's debug it. And there we are, we're on our no-op. Now I'm going to click the continue button instead of the step over, and that will take me to my next breakpoint. So we're going to put all F's into EAX. And now let's put 3333, which is 16 bits, 4 nibbles. 4 nibbles times 4 bytes a nibble is 16 bits. We're going to put 3333 in AX, which should be the lower half. And there it is. So half of EAX has changed. The upper half is not. And that's our register demonstration. Now you can do this with the EBX. I could go in here and change EAX to EBX, change all the A's to B, and it'll work exactly the same. Except now we're not going to be looking at EAX, we're going to be looking at EBX. So we're going to be looking at this one right here. And we can just step over. And now EBX is changing instead of EAX. All right, so let's take a look at a 64-bit version of this demonstration. All right, we just finished the 32-bit demonstration. Let's take a look at the 64-bit demonstration. It's going to be a lot like the 32-bit. I'm going to create a new project. This time I'm going to create a Komanetsky's function 64-bit. There it is right there. And I'm going to call this one 64-bit register demo. Open up the source file. Now 64-bit is by default, so we don't have to worry about changing it to x86, which we had to the last time. So it's kind of a pain in the neck. I'm going to go ahead and just get rid of all of the stuff we don't need. I should have probably given you guys a better template, but this template shows you how to start using the Komanetsky functions. So let's go ahead and get rid of all of that. Pretty good. Okay. So let's do the same thing with 64-bit that we did with 32-bit. So in the 64-bit, we got a lot more nibbles. So it's 8 bytes. 8 times 2 is 16, so we have 16 nibbles. So let's move into RAX, 16 nibbles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's move into AL, 1, 1. Let's move into AH, 2, 2. Let's put some more code in here. Let's move into AX, 1, 2, 3, 4. Oh, let's put an H at the end of these. So 1, 2, 3, 4. That's AX. And then let's move into EAX. 1, 2, 3, 4, 5, 6, 7, 8, H. Now, the reason why we're doing that is because there's a special thing about EAX, is that if you move some value into EAX, it's going to change all of RAX. It's going to move all those 4s in this case into the bottom half of RAX, but then it's going to put 0s in the upper half. And that's the way it's been happening for a long time as I've been teaching this. Let's make sure it's still doing it that way. So I'm going to go ahead and build the solution. Okay, I'm going to go up to line 10, debug, toggle breakpoint, and now let's debug it. Okay, notice that we've got R's instead of E's. Also notice we have a bunch more registers down here. Now, if you don't see this, make sure you go to Debug, Windows, and Registers, and you'll get this tab. So many more general purpose registers that you can play with. So let's go ahead and debug this. Okay, let's move all F's to RAX. There you go. RAX is in the red. That's one nice thing about Visual Studio Debugger. It highlights the registers that change. Also, I wanted to show you something else that we didn't look in the 32-bit version is the instruction pointer. RIP, EIP in 32-bit, that changes every time you execute a line of code because the instruction pointer is pointing to each line of code to let the CPU know this is where you are, this is the next thing to execute. Okay, now I can expand the, actually, can I? Yeah, I don't, doesn't, yeah, there we go. So I can expand my registers window a little bit there. All right, so now we're going to put 11 into AL, and that should affect the bottom 2 nibbles of RAX, which it did. Now let's put 22 in the upper 2 nibbles. There's the 22. We're going to put 3333 into the lower 16 bits. There it is. Now watch what happens when I move all 4s into EAX. It zeroes out everything to the left. So this is something really different in the 64-bit. And I believe they did that for compatibility purposes, to make it easier for developers to convert from 32-bit to 64-bit. So that's it. That's actually how the 64-bit registers work. I could actually change, I'm going to stop the debugging here. I could actually change all these to, let's say, I don't know, R10. Now, the problem with this is that there is no lower 8 bits, no upper lower 8 bits, no lower 16 bits. These are 64-bit registers. So we can't do this whole demo with the R8, 9, 10, those registers, because only the RAX, RBX, RCX, and RDX registers are separated into those sub-registers. But you could use those. I could go ahead and just, let's put a whole bunch of data in there. So I'm going to move into R10. I can just go ahead and do the same thing. And I'm not going to, like I said, there are no sub-registers, so I really can't do anything with that. I'm going to start the debugging. And we're going to be looking at R10, which is, where is that guy? That's right here. So let's go ahead and step through our code. And there's R10. And if you were paying attention, if you were noticing the RIP, it changes. In fact, let's go ahead and do that. I'm going to go ahead and step over and let's watch the rest in peace. Let's watch the instruction pointer, and it's going to go from F7, it's going to be incremented to 201. So that means that line 27 is a certain number of bytes long, and the instruction pointer changes every time we go to the next line of code, and that's how the CPU knows which line of code it is in your program. All right, great. So let's go ahead and stop our code. And what's next is that I'm going to do a demonstration on Linux, and it's going to be a very quick demonstration, but it's a demonstration to show you just how compatible assembler is across both Windows and Linux. It's just a different assembler. Hey, welcome back to my registers video, and where we are right now is we're going to demonstrate doing the registers on Linux. We just did it on Windows. Let's demonstrate it on Linux. So I'm going to go into my home directory. I'm going to go into documents. I put all of my templates in ASM projects. And this time, let's go ahead and do the 32-bit functions template. So I'm going to right click on that and extract here. There we go. Oh, I should always rename that. So x86 registers demo. And I always like to rename them because then I like to zip them up and put them in my archive of demonstration applications, so I can use that code later on. All right, great. So let's go ahead and let's look at main.asm, and let's basically do exactly what we did in the Windows version. So I'm not going to put anything in the data version, and I'm going to go down here in the code, the data section. I'm going to go down here in the code section, and let's start moving some data. So I'm going to move into EAX. Let's move all Fs. Let's move into AL. 11H, let's move into AH, 22H, let's move into AX, 3333H. Let's save and build that. I like to build things from the command line because I can execute them right away. So I'm just going to go ahead and say make. There, it ran fine. Now I'm going to debug it with KDBG. Oh, I created a new KDBG video out there, how to install KDBG on your Linux if the sudo apt install KDBG does not work. It's a great video. Take a look at it. And there's my output window. Here's my KDBG debugger. And let's put a breakpoint on the no-op. Actually, let's put a breakpoint down here on the move. I like to put them in multiple places. And let's start it. I'm going to click on run again to jump over the print. And if you go back to your terminal, you can see the print right there. Okay, so we have our registers pane down here already open. Let's step over. EAX has all Fs in it. That's great. AL is now going to get 11. You can see 11 on the far right. 22 is going to be put into AH, which should be just to the left of AL, the 11. There we go, 22. I'm going to move all threes into EAX, and you can see how the bottom half of EAX, which is AX, has been modified. Okay, let's complete that. We can see on our output it ran okay. Let's close the debugger. Now let's quickly go in here and do a 64-bit version. Now, if you didn't do the Windows demo, go ahead, go back in this video and take a look at the Windows because we were more detailed about it. And I'm trying to keep these videos down to a certain size or a certain amount of time. Okay, so let's go ahead and do it on 64-bit. I don't know if you're noticing, but it's a lot quicker developing under Linux. It just is. Once you get used to it, it's just so much faster. All right, so I'm going to right-click on the ASM. I'm going to open it with Genie. I know I probably upset some people saying that. Okay. All right, so let's move into RAX. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's move into AL11H. Let's move into AH 22H. Let's move into AX 3333H. And then let's move into EX 1, 2, 3, 4, 5, 6, 7, 8. Basically what we did on Windows. Okay. Let's right click on the background, open in terminal, make KDBG main. Let's put our no-op right here. I also want to put them on my first move. Run it. Run it. All right, so let's move all F's into RAX. And I can change the size of this a little bit. There we go. Step over, AL. You can see the bottom two nibbles have been updated at 11. The two nibbles to the left have been updated to 22, and we put them into AH. 3333 going to AX, which is the bottom 16 bits. And now let's put all fours into EAX, and it zeroes out everything to the left of EAX. So those other 8 nibbles are zeroed out. Now the reason that you don't see all zeros there is because this particular debugger does not show leading zeros. All right. Let's do one more thing on the Linux. Let's debug this with the DDD debugger. And DDD is a lot like KDBG. It's not as pretty, but if you haven't installed KDBG, it might not be a bad idea to figure out how to do this. So what I'm going to do is I'm going to put a breakpoint. By right-clicking on the line, I'm going to say set breakpoint. Now we have a little breakpoint there. It has a little word stop in there. And I'm going to say run. Okay, so we have the little arrow. Now, the thing about this debugger, it's a little bit different. I'm going to go up to status registers, and we kind of see the registers in a pop-out window. I have had some students like this better than KDBG because you can have multiple windows all over the place. So whatever you like, it's all. And now I'm going to say step, and you can see all F's in RAX. I'm going to say step. You can see the 11 in the far right 2 nibbles, step. You can see the 22 and the far right 2 nibbles to the left of that, step. There's the 3333 in AX. There's the 444, 44444 into EAX, and it's zeroed out everything to the left. And if you watch the instruction pointer, is the instruction pointer there? Yeah, it's a little bit different. Let's see if we have the instruction pointer. Here's our instruction pointer right there. And as we step through it, the instruction pointer changes its value. All right, so the program is done in the DDD debugger. All right, that is our Linux demo. Hey, welcome back from the demonstrations. A little bit more lecture here. Let's take a look at the flags register. I mentioned this earlier in the first part of this video. The flags register is how the status of the CPU is kept. Where all of the, was there a carry? Was there an overflow during a mathematical calculation? Is there a problem? What is the status of the CPU? And that's using what we call the E-flags register. E-flags carries a bunch of bits, and if the bit is turned on, that condition is set. So if there was a carry, which we're going to learn about more and more, if there was a carry, then the carry bit is turned on. It's a 1. If there wasn't a carry, the carry bit is turned off, which is a 0, and that normally happens during arithmetic. So the bits are set up like this. Bit 0, the far right bit, the least significant bit, is the carry flag. Bit 2 is the parity flag. Bit 6 is the 0 flag. Bit 7 is the sign flag. And bit 10 is the overflow flag. Those are the most common used flags in the E-flags register. There are additional, but they're not that often used by the programmer. The parity bit might be used, and we're going to talk about that in a little while. But those are the bits that are most commonly used. So the carry flag, if you add 2 unsigned numbers that and there aren't enough bits to contain that addition, the carry flag will be turned on because a 1 got lost. If you remember when we did binary arithmetic, if you add FFFF, a 1 goes into the third bit. Well, or the third nibble. Or no, it's the third bit. No, it's the third nibble. So if you only have 2 nibbles and you need a third nibble in your mathematical calculation, the carry bit's going to turn on. Now that's for unsigned numbers. If you have a signed number, the overflow flag will be turned on. And I also like to say that the overflow flag will be turned on if a nonsensical result occurs from your mathematics. So like if I add 2 positive numbers and which results in a negative number, That doesn't make any sense, so the overflow flag will be turned on. If I multiply two negative numbers and I get a negative result, that's a nonsensical result, so the overflow flag will be turned on. The zero flag will be turned on if the result of your mathematical calculation is the number 0. So if I take 1 times 0, 1 multiplied by 0, that's a 0 result. The 0 flag will be turned on. The sign flag will be turned on if your mathematical calculation results in a negative number. So if I multiply 10 multiplied by 2, negative 2, that's going to be a negative 20, so the sign flag will be turned on. The parity flag is turned on if an instruction results in an even number of on bits. So let's say if I have 0, 1, 1, 1, that's an odd number of on bits, and if I add 1 to it, or if I add 1, 0, 0, 0. So if I take 0, 1, 1, 1, and if I add 1, 0, 0, 0 to it, that's going to be 1, 1, 1, 1. That's an even number of bits, so the parity flag will be turned on. If it's an odd number of bits, it'll be turned off. And here's a whole bunch of the other flags. Some of them bits. Some of them may not be listed here. Like I don't think bit number 2 is listed there, is it? Or bit number 1. Bit number 1 isn't listed in there because it's probably a reserved bit that's used by the CPU that a programmer has no interest in. But here's a bunch of other ones: auxiliary carry flags, interrupt enable, a whole bunch of other ones you probably will never use. So, but they're there for you to know what's going on. And that's it. So those are the registers of the CPU. What I recommend you doing is creating your own either Visual Studio or Linux assembly language program, playing around with the registers, trying different ones. I'm going to be exposing you guys to a lot of stuff with the registers, and so you're going to get a lot of practice. But try it out yourself. That's the fun of programming. All right, great. Hope to see you at the next video.